This is a technical archive of the automated car wash. Before we begin our journey through the 3,050 RPM reciprocating pumps and the fluid dynamics of the wash bay, please subscribe and join our archive. It is the best way to ensure these mechanical histories are preserved. Now settle into your seat and close your eyes as we enter the Valley Vista car wash. The evening shift begins at precisely 6:47 p.m. The fluorescent lights hum to life with a soft, steady tone at 60 Hz, creating a baseline rhythm that will accompany us through the next 2 hours. This is not just any car wash. This is a symphony of infrastructure. A carefully orchestrated dance of pumps, brushes, nozzles, and reclamation systems that process an average of 47 vehicles per hour. Let us begin at the heart of it all. At the center of bay number 3 sits the primary high-pressure reciprocating pump. It is a CAT 3560 model, installed in March of 2019, and it has been running with metronomic precision ever since. The pump operates at 3,450 revolutions per minute, driven by a 35 horsepower electric motor that draws 26.8 amps at 230 volts, 3-phase power. The pump itself weighs 187 pounds and sits on a vibration-dampening mount made of molded rubber composite, measuring 14 inches square and 3 inches thick. These mounts reduce operational vibration by 94%, transforming what could be a harsh mechanical clatter into a smooth, almost meditative hum. Inside the pump housing, 3 ceramic-coated plungers move in perfect synchronization. Each plunger has a diameter of 0.875 inches and a stroke length of 1.2 inches. They reciprocate, forward, back, at that constant 3,450 cycles per minute. That's 57.5 strokes every single second, creating a rhythm so fast it blends into a continuous tone, like the lowest note on a pipe organ mixed with distant thunder. The whoosh begins here. Water enters the pump at municipal pressure, approximately 65 pounds per square inch from the city main line. The pump takes this water and pressurizes it to 1,200 psi. This transformation happens in fractions of a second in the tiny chambers between the plungers and the stainless steel valves. Each chamber can hold exactly 2.3 cubic inches of water. As the plunger pushes forward, the water has nowhere to go but out, forced through brass check valves that open and close with mechanical precision. The sound of these check valves is like a rapid heartbeat, but deeper, more resonant. Click, 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 57 times per second, creating a texture of sound that your ear perceives not as individual clicks, but as a rich, layered hum. It's the sound of controlled power, of pressure building and being released in perfect rhythm. The pump delivers 5.5 gallons per minute at full pressure. Over the course of an hour, that's 330 gallons. Over a typical 10-hour shift, 3,300 gallons of water pass through this single pump, transformed from gentle municipal flow into powerful, directed streams capable of removing road grime, brake dust, and the accumulated debris of 1,000 miles of highway driving. The motor that drives this pump produces its own symphony. The SAM, 3-phase power, creates a rotating magnetic field inside the motor housing, spinning at exactly 1,725 revolutions per minute before being geared up to the pump's 3,450 RPM requirement. The gear ratio is precisely 2:1, achieved through a robust helical gear set submerged in ISO 68 weight gear oil. The gears mesh with 94% efficiency, creating a gentle whirring sound like wind through distant pines, steady and eternal. As the pump runs, you can feel its presence even from 20 feet away. Not as vibration, those rubber mounts see to that, but as a subtle pressure change in the air, a sense of purposeful energy being directed and controlled. The air around the pump is warmer by exactly 3.7 degrees Fahrenheit due to the motor's operation, creating gentle convection currents that rise toward the ceiling of the equipment room. The equipment room itself is 12 feet by 16 feet with 8-foot ceilings. The walls are lined with sound-dampening foam panels 2 inches thick with an NRC noise reduction coefficient of 0.85. This means that 85% of sound energy is absorbed rather than reflected, creating an acoustic environment that is full, but not harsh, present, but not overwhelming. It's like standing inside a drum that's being played very, very softly. The pump's discharge line is 3 4-inch stainless steel, Schedule 40, rated for 3,000 psi, more than twice what it needs to handle, because infrastructure should always exceed requirements. The water flows through this pipe at a velocity of 12.3 feet per second. You can hear it if you press your ear against the pipe. A smooth, rushing sound, like a river compressed into a cylinder of steel. Every 17 seconds, the pump's pressure switch cycles, maintaining system pressure between 1,180 and 1,220 psi. When pressure drops to 1,080, the switch clicks on with a soft snap. When it rises to 1,220, another soft snap signals the switch to idle the motor down to minimum speed. This cycling is so subtle, so gentle, that most people would never notice it. But if you pay attention, if you truly listen, you can hear the slight change in pitch, the minor variation in the hum that tells you the system is alive and responding. The pump runs in a continuous cycle. Prime, pressurize, deliver, maintain. Prime, pressurize, deliver, maintain. Over and over, thousands of times per day, millions of times per year. It is designed for 20,000 hours of operation before requiring major service. At current usage rates, that's approximately 7 years of faithful service. Tonight, in bay number 3, a silver Honda Civic enters the Whoosh tunnel. The entry sensor, a photoelectric beam operating at 940 nanometers in the near-infrared spectrum, detects the vehicle's presence. The sensor sends a 24-volt DC signal to the programmable logic controller, a compact unit no larger than a shoebox, which begins the Whoosh sequence. The high-pressure pump receives its command. The motor spools up from idle to full speed over a period of 1.3 seconds, a smooth acceleration that prevents water hammer in the lines. The hum deepens, intensifies, becomes more present, and then the first nozzle opens. The pre-soak arch stands 7 feet tall and spans the full width of the Whoosh tunnel, which is precisely 9 feet, 4 inches at its narrowest point. The arch contains 42 nozzles arranged in 3 rows, 14 nozzles on each side and 14 across the top. Each nozzle is a marvel of micro-engineering. The nozzle bodies are machined from 316 stainless steel, chosen for its resistance to the alkaline chemicals used in car washing. Each nozzle has an orifice diameter of 0.040 inches, about the thickness of a standard paperclip wire. Through this tiny opening, water at 1,200 psi emerges at a velocity of 186 feet per second. That's faster than a professional baseball pitcher's fastball. That's 127 miles per hour, condensed into a stream no wider than a pencil lead. When 42 of these streams activate simultaneously, the sound is extraordinary. It's not a simple whoosh. It's a chord, a complex harmonic structure made of overlapping frequencies. The fundamental tone is around 220 Hz, close to an A note on a piano, but layered on top are overtones, harmonics, the sound of water atomizing as it exits the nozzle, breaking into millions of microscopic droplets that catch the fluorescent, light, and create a fine mist that hangs in the air. The pre-soak solution is stored in a 275-gallon intermediate bulk container made of high-density polyethylene. The solution is a carefully formulated blend: 12% surfactants, 3% chelating agents, 2% alkaline builders, and 83% water. This mixture has a pH of 11.2, alkaline enough to break down oils and greases, but not so harsh as to damage paint or rubber seals. A dedicated pump, a centrifugal model spinning at 1,750 RPM, draws this solution from the tank and meters it into the water. Stream at a ratio of 1.120. For every 120 parts of water, 1 part of pre-soak concentrate. This mixing happens in a Venturi injector, a simple but elegant device with no moving parts. The water flows through a constricted section, creating a low-pressure zone that draws the chemical concentrate into the stream through a side port. Physics does all the work. The Venturi injector hums at a frequency determined by the flow rate and the dimensions of the constriction. Tonight, It's producing a tone at approximately 380 Hz, a slightly higher pitch than the water streams themselves, creating an acoustic beating pattern, a gentle wah-wah-wah-wah that pulses at about 4 cycles per second. It's hypnotic, this pulsing, like a slow heartbeat made of water and chemistry. The pre-soak solution hits the Honda Civic in overlapping patterns. The 14 side nozzles are aimed at precisely 23 degrees from horizontal, calculated to provide optimal coverage of the vehicle's lower panels, wheel wells, and rocker panels, the areas where road grime accumulates most heavily. The top 14 nozzles point straight down, covering the hood, roof, and trunk. The spray patterns overlap by 30%, ensuring that no area receives less than full coverage. The dwell time, the period during which the pre-soak remains on the vehicle before being rinsed, is calibrated to 45 seconds. This is not arbitrary. Laboratory testing has shown that the surfactants in the pre-soak formula require 38 seconds to fully penetrate and emulsify road film. 45 seconds provides a 7-second safety margin, accounting for variations in temperature and grime thickness. During these 45 seconds, the conveyor system continues to move the vehicle forward at a precisely controlled rate of 2.6 feet per minute. The conveyor is a roller system with polyurethane-coated rollers spaced every 18 inches along a 40-foot tunnel. Each roller is powered by a 1.2 horsepower motor through a chain drive system, creating a synchronized movement that is smooth and vibration-free. The sound of the conveyor is a low rumble, felt as much as heard. The roller motors produce a collective hum at 60 Hz, the same frequency as the electrical supply, but the chain drives add a subtle rhythmic component, a soft ch-ch-ch-ch as each link engages and disengages with the sprockets. There are 147 links in each chain section, and with the roller turning at 23 RPM, each link passes through the sprocket 3,181 times per hour. This creates a sonic texture, a granular quality to the sound that is oddly soothing, like distant rain on a tin roof. The Honda Civic moves forward, now 6 feet into the tunnel, its surface covered in a thin film of pre-soak solution. Tiny droplets run down the windows, following paths determined by gravity and surface tension, creating ephemeral streams that reflect the overhead lights in shifting, complex patterns. Now we arrive at the first brush, and this is where the wash becomes tactile, where chemical cleaning transitions to mechanical cleaning. The brush assembly is a rotating cylinder, 5 feet in diameter and 7 feet long, covered in thousands of individual foam bristles. But these are not ordinary bristles. Each bristle is made of closed-cell polyethylene foam, extruded through a die at precisely 340 degrees Fahrenheit, and then cooled in a water bath over a period of 12 seconds. This process creates a foam structure with cells that are 0.4 millimeters in average diameter, small enough to trap and remove dirt particles, but large enough to remain soft and flexible. The closed cell structure means that water and chemicals cannot penetrate into the foam, preventing the bristles from becoming waterlogged and heavy. The bristles are arranged in a helical pattern around the brush cylinder, with each bristle offset from its neighbors by 3.7 degrees of rotation. This creates a continuous, overlapping pattern of contact with the vehicle surface. There are exactly 1,296 bristles on this brush, 144 rows of 9 bristles each. The number is not accidental. It provides the optimal balance between cleaning effectiveness and brush longevity. The brush rotates at 125 RPM. This is a critical specification. Too slow, and the bristles don't generate enough scrubbing action to remove bonded contaminants. Too fast, and the bristles can create swirl marks in the paint's clear coat. 125 RPM is the sweet spot, determined through years of testing with paint thickness gauges and surface profilometers. At 125 RPM, each bristle makes contact with a given point on the vehicle surface 20.8 times per second. But the bristles are soft. They compress by up to 60% of their length when pressed against a surface. This compression means that each contact is gentle, more of a caress than a scrub, yet effective because of the sheer number of contacts occurring simultaneously. The brush is driven by a 5-horsepower motor through a gearbox with a 14.1 reduction ratio. The motor spins at 1,750 RPM, and the gearbox reduces this to exactly 125 RPM while increasing torque proportionally. The gearbox is a planetary design, with 3 planet gears orbiting a central sun gear, all enclosed in a housing filled with synthetic lubricant. The gears produce a soft whirring sound, a mechanical purr that blends with the deeper hum of the motor. As the brush makes contact with the Honda Civic, the sound changes. The foam bristles compress against the sheet metal of the hood, and you hear a soft swooshing sound, like corduroy being stroked in rhythm. Swoosh, 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 125 times per minute, while simultaneously each individual bristle adds its own tiny contribution to the sonic texture. It's a white noise, but with structure, with pattern, with intention. The brush moves laterally as it rotates, traveling along a horizontal rail that spans the width of the wash tunnel. This lateral motion is controlled by a servo motor and a precision ball screw assembly. The brush travels from the driver's side of the vehicle to the passenger side at a rate of 6 inches per second, ensuring complete coverage of the hood, roof, and trunk. When it reaches the end of its travel, a limit switch signals the servo to reverse direction, and the brush travels back across the vehicle at the same steady rate. This back-and-forth motion creates a Doppler effect in the sound. As the brush approaches, the pitch rises slightly, perhaps by 15 or 20 hertz, barely perceptible, but definitely present. As it moves away, the pitch drops by a corresponding amount. This gentle pitch modulation adds another layer of complexity to the soundscape, a subtle variation that prevents the audio from becoming monotonous. The brush assembly contains its own dedicated water supply system. 8 nozzles, embedded within the brush cylinder and protected by the foam bristles, deliver a steady stream of fresh water at 40 psi, much lower pressure than the pre-soak arch, because the purpose here is to lubricate and rinse, not to blast. The water flows at 2.2 gallons per minute, creating a gentle splashing sound as it mixes with the pre-soak solution being scrubbed from the vehicle's surface. Beneath the brush, a series of drain channels collect the runoff. These channels are molded fiberglass, sloped at exactly 2 degrees to ensure gravity-driven flow toward the collection sump. The water flows over the smooth fiberglass surface with a soft gurgling sound, like a small brook over rounded stones. This is not turbulent flow. The Reynolds number is around 1/800, placing it in the transitional region between laminar and turbulent flow, creating a complex acoustic signature that is part babble, part whisper. The Honda Civic spends 90 seconds under the first brush. During this time, the brush makes approximately 240 complete passes across the vehicle's upper surfaces. Each pass removes a microscopic layer of loosened grime, building incrementally toward a clean surface. It's a process that requires patience, repetition, and precision. As the Honda Civic continues its journey through the tunnel, it encounters the side brushes. These are vertical cylinders, 3 feet in diameter and 6 feet tall, positioned on both sides of the wash bay. Like the top brush, they are covered in closed-cell foam bristles, but these bristles are slightly longer, 4 inches instead of 3, to accommodate the irregular contours of doors, fenders, and quarter panels. The side brushes rotate at 145 RPM, slightly faster than the top brush. This higher speed compensates for the fact that they make contact with a smaller surface area at any given moment. The increased rotational velocity ensures that the scrubbing action remains consistent across all surfaces of the vehicle. These brushes also oscillate vertically, rising and falling through a range of 14 inches to follow the contours of the vehicle. The oscillation is controlled by a pneumatic cylinder operating at 80 psi. The cylinder extends and retracts once every 2.3 seconds, creating a slow, rhythmic up and down motion. You can hear the air pressure equalizing in the cylinder with each stroke. A soft, like gentle breathing, perfectly synchronized between the left and right sides. The sound of the side brushes is different from the top brush because of the angle of contact. The bristles strike the vertical surfaces of the vehicle at approximately 90 degrees, creating a slapping sound rather than a swooshing sound, Slap, 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 145 times per minute, but softened by the foam, muted by the water, transformed into something rhythmic and soothing rather than harsh. Now we come to one of the most satisfying elements of the entire car wash: the wheel cleaning system. This is a specialized subsystem designed to clean the wheels and wheel wells, areas that accumulate significant amounts of brake dust and road grime. The wheel cleaning system consists of high-pressure nozzles positioned at axle height, aimed directly at the wheels. These nozzles operate at the full 1 to 200 psi provided by the main pump system, but with a different nozzle configuration. Instead of the 0.040-inch orifices used in the pre-soak arch, these nozzles have 0.025-inch orifices, smaller, creating even higher velocity streams. Water exits these nozzles at 244 feet per second. That's 166 miles per hour. That's fast enough to strip away layers of brake dust that have been baked onto the wheel surface by repeated heating and cooling cycles. The sound is sharper, more focused than the pre-soak arch. It's a high-pitched scream that drops in frequency as the water loses velocity, creating a sound like a distant jet engine, constant but not overwhelming. The wheel cleaning system uses a specialized chemical, an acid-based wheel cleaner with a pH of 2.8. This is much more acidic than the pre-soak solution, formulated specifically to dissolve iron oxide, rust, and other metallic contaminants that accumulate on wheels. The acid is safe for aluminum and steel wheels, but aggressive enough to remove even stubborn staining. This acid is injected into the water stream through a separate metering pump, a diaphragm type that operates at 60 strokes per minute, driven by a small electric motor. Each stroke of the diaphragm displaces 0.12 fluid ounces, creating a pulsed injection that is visible as slight variations in the opacity of the water stream. The pump produces a rhythmic clicking sound, softer than the high-pressure pump but still distinct. Click, 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 click once per second, a steady metronome underlying the higher frequency sounds of the water jets. The wheel wells are cleaned by a separate set of nozzles, positioned higher and aimed upward into the recessed areas above and behind each wheel. These nozzles use a fan pattern rather than a focused stream, spreading the water across a wider area to reach all the complex surfaces inside the wheel well. The fan pattern creates a different sound signature, less of a focused scream, more of a broad swoosh like wind through leaves. During the wheel cleaning cycle, which lasts 30 seconds, the conveyor briefly pauses. This is necessary to ensure that the high-pressure streams have sufficient time to work on each wheel. The pause is controlled by the programmable logic controller, which monitors the position of the vehicle using a series of photoelectric sensors spaced along the tunnel. When the conveyor pauses, the background sound changes. The continuous rumble of the roller stops, and in the sudden absence of that foundational tone, the other sounds become more prominent. You can hear the high-pressure pump more clearly now, its steady 60 Hz hum filling the acoustic space. You can hear the ventilation system, which runs continuously, pulling humid air from the wash tunnel and exhausting it outside. The ventilation fans are centrifugal blowers, moving 1,200 cubic feet of air per minute, creating a gentle breeze that you can feel on your skin and hear as a soft, constant sigh. Then, after exactly 30 seconds, the conveyor resumes. The roller motors engage with a barely perceptible bump, and the Honda Civic continues forward at its steady 2.6 feet per minute. The wheel cleaning nozzles deactivate, their high-pressure streams cutting off with a sharp shunk sound as the solenoid valves close. The silence after the scream is profound, a moment of relative quiet before the next stage begins. Before we move to the rinse cycle, we must pause to appreciate one of the most impressive pieces of infrastructure in the entire facility, the water reclamation system. This is the environmental heart of the car wash, the component that makes the entire operation sustainable. Every drop of water that has been used so far, the pre-soak, the brush water, the wheel cleaning solution, flows down through the floor, drains into a collection sump located beneath the wash tunnel. This sump is a concrete basin, 8 feet deep, 10 feet wide, and 40 feet long, with a total capacity of 2,400 gallons. Water enters the sump through 6-inch diameter drain pipes, creating a constant flow that maintains the water level between 6 and 7 feet deep. The sump is not just a collection point, it's the first stage of the reclamation process. At the bottom of the sump, settled sediment accumulates, sand, grit, small gravel particles that have been washed from vehicles. This sediment layer is automatically removed once per day by a sludge pump, a specialized unit that can handle high solids content without clogging. The sludge is pumped to a settling tank where it's allowed to dewater, and then it's disposed of as non-hazardous solid waste. But this is a small fraction of the total water. Most of the water will be reclaimed and reused. The reclamation pump is a centrifugal model rated for 100 gallons per minute. It draws water from the sump through a 6-inch intake pipe, and this is where the real work begins. The pump operates continuously during business hours, maintaining constant flow through the reclamation system. First stage, coarse filtration. The water passes through a drum filter with 200-micron stainless steel mesh. This removes larger particles, bits of leaves, gravel, anything bigger than 0.2 millimeters. The drum rotates slowly at 4 RPM. And as it rotates, a spray bar positioned on the backside continuously rinses the accumulated debris from the mesh, flushing it to a waste stream that represents about 5% of the total flow. The sound of the drum filter is mechanical and rhythmic. The drum is 7 feet in diameter, so at 4 RPM, it completes 1 revolution every 15 seconds. As each section of the mesh passes the spray bar, you hear a brief intensification of the water sound, shh, 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 15 seconds apart, marking time like a very slow clock. Second stage, fine filtration. The water flows into a sand filter vessel, a fiberglass tank 6 feet in diameter and 8 feet tall, filled with 3,200 pounds of filter sand. The sand is not ordinary beach sand. It's manufactured filter media with controlled particle size distribution ranging from 0.45 to 0.55 millimeters in diameter. Water enters at the top of the sand filter and percolates down through the sand, bed at a filtration rate of 12 gallons per minute per square foot of filter area. The sand removes particles down to approximately 20 microns, about 1/4 the diameter of a human hair. This is fine enough to remove most suspended solids, leaving the water visually clear. The sand filter operates under pressure, maintained by the reclamation pump. Inside the filter vessel, the pressure is 25 psi, enough to drive water through the sand bed, but not so high as to compact the sand and reduce flow. You can't hear the filtration process itself. It's silent, a purely physical process of water weaving through the spaces between sand grains, but you can hear the water flowing into and out of the filter vessel through the connected piping. Every 72 hours, the sand filter undergoes backwashing. This is an automatic process controlled by a timer. During backwashing, flow is reversed. Water is pumped upward through the sand bed at high velocity, fluidizing the sand and flushing accumulated debris out through a waistline. Backwashing lasts for 8 minutes and consumes approximately 250 gallons of water, but it's necessary to maintain filtration efficiency. Third stage, biological treatment. This is where the car wash separates itself from lesser operations. The filtered water flows into a biological reactor, a tank containing specialized bacteria that consume organic compounds, oils, greases, detergents, breaking them down into carbon dioxide and water through natural metabolic processes. The biological reactor is aerated, meaning that air is continuously bubbled through the water to provide oxygen for the bacteria. The air is supplied by a regenerative blower, a device that looks like a large metal cylinder with a motor on one end. The blower operates at 3,450 RPM and delivers 60 cubic feet of air per minute at 4 psi. The blower produces a distinct sound, higher pitched than the pump motors, at around 400 Hz. It's a steady tone, almost musical, like a sustained note on a clarinet. The air exits the blower through a pipe and enters the biological reactor through a diffuser manifold at the bottom of the tank. The diffuser has dozens of tiny pores, creating millions of microscopic bubbles that rise through the water column. The sound F-aeration is one of the most soothing in the entire facility. It's a gentle fizzing, like carbonation in a freshly poured soda, but sustained indefinitely. The bubbles rise through 20 feet of water, creating a curtain of sound that is both white noise and melodic tone. Standing next to the biological reactor, you can hear layer upon layer of bubbles, each cluster rising at slightly different rates, creating interference patterns in the sound that wax and wane in a slow, complex rhythm. The bacteria in the reactor consume approximately 95% of the organic load in the water over a retention time of 4 hours. The water emerges from the biological reactor clean enough to reuse in the car wash, though not clean enough to discharge to the environment. For reuse, it's perfect. Fourth stage, clarification. The biologically treated water flows into a clarifier tank, where any remaining suspended solids settle out under the influence of gravity. The clarifier is a cone-bottom tank, 12 feet in diameter at the top and tapering to 18 inches at the bottom. Water enters at the center and flows radially outward, slowing down as the flow area increases, allowing particles to settle. The clarified water is drawn from the top of the tank through a weir, a carefully leveled edge over which the water flows in a thin sheet. The sound of water flowing over the weir is like rain on water, a soft pattering that varies slightly with the flow rate. When the reclamation system is processing a full 100 gallons per minute, the weir produces a sustained, gentle splashing that is almost hypnotic in its constancy. The settled solids at the bottom of the clarifier are periodically removed by a scraper mechanism that rotates slowly, one revolution every 20 minutes, pushing the solids toward a central sump where they're pumped out for disposal. The scraper is driven by a small gear motor, and you can hear it turning. A soft, mechanical grinding, muted by the water, marking the passage of time in 20-minute intervals. From the clarifier, the reclaimed water flows to a storage tank, a 1,500-gallon capacity vessel that serves as a buffer between the reclamation system and the wash operations. This tank ensures that there's always clean, reclaimed water available for use, even during peak demand periods. The reclamation system recovers approximately 85% of the water used in the wash process. Of the 100 gallons per minute flowing into the wash tunnel, 85 gallons per minute are reclaimed, treated, and reused. The remaining 15 gallons per minute are lost to evaporation, carry out on vehicles, and waste streams from the filtration processes. This 15 gallons per minute must be replaced with fresh city water, but it's a dramatic reduction compared to the 100 gallons per minute that would be required without reclamation. The environmental impact is substantial. Over the course of a year, this single car wash processes approximately 1.5 million gallons of reclaimed water. That's 1.5 million gallons that don't need to be drawn from municipal supplies. 1.5 million gallons that don't need to be treated at the water treatment plant. It's infrastructure doing what infrastructure does best, working invisibly, efficiently, sustainably, to provide a service while minimizing environmental impact. The Honda Civic emerges from the foam brush section, its surface clean but covered in a film of water containing dissolved minerals, calcium, magnesium, iron, the components of water hardness. If this water were allowed to dry on the vehicle, it would leave spots, white mineral deposits that mar the finish. This is where the spot-free rinse system comes into play. The spot-free rinse uses water that has been demineralized to a resistivity of 1.0 megom centimeter. This is very pure water, essentially distilled, with almost no dissolved solids. When this water dries, it leaves no residue, no spots, just a clean, clear surface. The demineralization is achieved through a reverse osmosis system, one of the most elegant pieces of chemical engineering in the facility. The system consists of a membrane module containing spiral wound membranes made of thin film composite polyamide. These membranes have pore sizes on the molecular scale, small enough to pass water molecules while rejecting dissolved ions. Feed water enters the membrane module at 200 psi, provided by a dedicated high-pressure pump. As the water passes through the membranes, pure water permeates through the membrane material and is collected in a central tube. The rejected ions remain on the feed side, becoming more concentrated as the pure water is removed. This concentrated solution, called the reject stream, is sent to the drain. The reverse osmosis system operates at a recovery rate of 75%, meaning that 75% of the feed water becomes product water and 25% becomes reject. For every 100 gallons of feed water, 75 gallons of spot-free rinse water are produced. This is an excellent recovery rate, achieved through careful control of pressure, temperature, and flow rate. The sound of the reverse osmosis system is primarily the sound of the high-pressure pump, a rotary vane model that operates more quietly than the reciprocating pumps used elsewhere in the facility. It produces a smooth, steady hum at 120 Hz, exactly double the frequency of the electrical supply due to the pump's design. This is a harmonic tone, pleasing to the ear, that blends with the other mechanical sounds to create a rich acoustic environment. The spot-free rinse is delivered through an overhead arch similar to the pre-soak arch but with fewer nozzles, 24 instead of 42, and larger orifice sizes, 0.060 inches instead of 0.040 inches. The larger orifices deliver water at lower velocity, creating a gentler rinse that doesn't disturb the cleaned surface. The pressure at the spot-free rinse nozzles is only 60 psi, compared to 1 to 200 psi for the pre-soak. This creates a completely different sound. Instead of a high-velocity scream, the spot-free rinse produces a softer, more diffuse sound, like rain on a tent. The droplets are larger, the spray pattern wider, the overall effect more soothing. The Honda Civic spends 40 seconds under the UA. Spot-free rinse arch, receiving approximately 20 gallons of demineralized water distributed evenly across all surfaces. The water flows down the windows, over the hood and trunk, following the contours of the vehicle in sheets that catch the light and shimmer like liquid glass. As the spot-free water flows off the vehicle, it too is collected in the floor drains and sent to the reclamation system. The reverse osmosis reject stream, concentrated with dissolved minerals, is sent directly to the sanitary sewer. This is necessary because the high mineral content would interfere with the biological treatment process if it were allowed into the reclamation system. The spot-free rinse system produces 45 gallons of product water per minute at design flow rate. The system operates only during actual rinse cycles, controlled by the programmable logic controller, so the average production rate is lower, approximately 20 gallons per minute when averaged over the entire operating day. The reverse osmosis. Membranes require replacement every 3 years, a major maintenance item that costs approximately $8,000 in parts and labor. But the membranes are essential to the operation, and their performance is monitored continuously. A conductivity meter installed in the product water line measures electrical conductivity, an indication of dissolved ion concentration, and if the conductivity rises above a preset threshold, an alarm sounds, and the system automatically switches to a backup membrane module while the primary module is serviced. The conductivity meter is a simple device. 2 metal electrodes in a flow chamber with an electronic circuit that measures the electrical resistance between them. Pure water has high resistance, around 1.0 megohm. As mineral content increases, resistance drops. The meter produces no sound, but it sends a 4 to 20 milliamp signal to the control system, a continuous stream of data representing water quality in real time. We now arrive at the final stage of the wash process, drying. This is accomplished by a series of high-velocity air blowers that direct sheets of air across the vehicle surface, pushing water off before it can form droplets that might leave spots. The drying system consists of 3 blower units positioned at the exit end of the wash tunnel. Each blower is a centrifugal fan driven by a 15-horsepower motor capable of moving 3,000 cubic feet of air per minute. The motors spin at 1,750 RPM and drive the fan impellers through a direct coupling, no belts, no gears, just a straight shaft connection for maximum efficiency. The sound of the blowers is the loudest element of the entire car wash, but it's not unpleasant. It's a roar, but a clean roar, like standing at the edge of a waterfall or near a jet engine at idle. The fundamental frequency is around 100 Hz, determined by the blade pass frequency, the rate at which the fan blades pass by a stationary point. With a fan impeller that has 16 blades spinning at 1,750 RPM, that's 467 blade passes per second, creating a tone at 467 Hz. But the fan also produces broadband noise, a rush of air that contains all frequencies, more or less equally, creating a white noise effect that masks other sounds and creates a sense of sonic immersion. The air exits the blowers through nozzles, shaped to create a flat, focused stream approximately 18 inches wide and 2 inches thick. The air velocity at the nozzle exit is 185 miles per hour. This is hurricane-force wind, controlled and directed with precision. The kinetic energy of this airstream is sufficient to shear water droplets off the vehicle surface and propel them outward, where they're captured by water collection troughs positioned on both sides of the tunnel. The blowers are positioned at 3 different heights, one aimed at the upper surfaces of the vehicle, one at the mid-level surfaces, and one in the lower surfaces and wheels. This ensures complete coverage with no area missed. The air streams overlap slightly, providing redundancy and ensuring thorough drying even for larger vehicles like SUVs and trucks. The Honda Civic spends 25 seconds in the drying zone, passing through the sequential airstreams. First, the upper blower, and you can see the water being blown off the roof and rear window, creating a spray of droplets that catches the light and creates momentary rainbows. Then, the mid-level blower, clearing the doors and side windows. Finally, the lower blower, targeting the rocker panels and wheels. The sound evolves as the vehicle moves through the blowers. When the airstream is hitting sheet metal, the sound is a deep buffeting, like fabric flapping in strong wind. When the airstream hits glass, the sound is higher pitched, more resonant. When the airstream hits rubber trim or tires, the sound is muted, absorbed by the softer material. As the vehicle exits the drying zone, the blowers automatically shut off, conserved through the photoelectric sensors that track vehicle position. The motors coast to a stop over a period of about 8 seconds, the roar gradually diminishing in pitch and volume until it fades to silence. In the absence of the blower noise, the background sounds of the facility reassert themselves. The RE in hum of the high-pressure pump, the gentle fizzing of the biological reactor aeration, the soft clicking of the chemical metering pumps. The Honda Civic rolls out of the wash tunnel, its surface clean and dry, ready for the driver to enter and depart. The entire process, from entry to exit, has taken 5 minutes and 47 seconds. In that time, the vehicle has been pre-soaked, scrubbed, rinsed, and dried, using a total of 42 gallons of water, 36 gallons of reclaimed water, and 6 gallons of fresh city water. Behind all of this mechanical symphony is the brain of the operation, the Programmable Logic Controller, or PLC. This compact device, about the size of a shoebox, contains a microprocessor running at 100 MHz, executing ladder logic programs that control every aspect of the wash sequence. The PLC receives inputs from dozens of sensors, photoelectric sensors that detect vehicle position, pressure transducers that monitor water pressure, flow meters that measure water usage, temperature sensors that ensure optimal chemical performance. Each of these sensors sends a continuous stream of data to the PLC, which processes this information and makes decisions in real time. When a vehicle enters the wash tunnel, the entry sensor sends a signal to the PLC. The PLC consults its program in logic and initiates the wash sequence. Activate the pre-soak pumps, open the pre-soak solenoid valves, start the conveyor, monitor vehicle position, activate the top brush motor, activate the side brush motors, initiate wheel cleaning, pause the conveyor, resume the conveyor, activate the spot-free rinse, activate the blowers, and so on through the entire sequence. Each of these actions is precisely timed. The PLC maintains an internal clock with microsecond accuracy, ensuring that each stage of the wash process receives exactly the right amount of time. Too little time, and the cleaning is inadequate. Too much time, and water is wasted. Chemicals are overconsumed, and throughput suffers. The PLC also monitors for faults. If a pump fails to start, if pressure drops below acceptable levels, If a sensor reports an out-of-range value, the PLC can halt the operation, sound an alarm, and display a diagnostic message on the operator interface panel. This fault detection is critical to maintaining uptime and preventing damage to vehicles or equipment. The operator interface is a touchscreen panel mounted on the wall of the equipment room. It displays the current status of all systems in real time. Pump pressures, flow rates, chemical levels, conveyor speed, blower status. The display updates 10 times per second, providing a continuously updated snapshot of the facility's operation. The PLC program itself is written in ladder logic, a graphical programming language that resembles electrical relay circuits. The current program is 2,847 lines long, representing hundreds of hours of engineering work. It includes algorithms for normal operation, startup sequences, shutdown sequences, diagnostic routines, and emergency stop procedures. The PLC communicates with the various motor drives, valve controllers, and sensors through industrial networks, using protocols like Modbus and Profibus. Data flows through shielded cables at rates up to 500 kilobits per second, fast enough to ensure that control actions happen within milliseconds of being commanded. There is no sound to the PLC's operation. It's an electronic device with no moving parts. But it is the silent conductor of this mechanical orchestra, coordinating the timing and sequencing of every component to create a seamless, efficient wash process. Let's take a closer look at the chemical systems that make the washing process effective. These chemicals are stored in a dedicated room adjacent to the wash tunnel, a climate-controlled space maintained at 68 degrees Fahrenheit to ensure optimal chemical stability. There are 5 primary chemicals used in the wash process, each stored in its own container. Pre-soak concentrate. Stored in a 275-gallon tote, alkaline formulation, pH 13.5 in concentrate form, diluted 1.120 for use. 2. Foam brush soap, stored in a 55-gallon drum, high foaming surfactant blend, pH 8.5, diluted 180 for use. Spot-free rinse conditioner, stored in a 15-gallon container, pH 6.0, used at a dilution of 1/1000 to enhance beading and sheeting action. Wheel cleaner, stored in a 30-gallon container, acidic formulation, pH 1.8 in concentrate form, diluted 1.10 for use. Drying agent, stored in a 15-gallon container, silicone-based polymer, used at a dilution of 1/500 to promote rapid water sheeting during the drying process. Each chemical is dispensed by a dedicated metering pump, precisely calibrated to deliver the correct dilution ratio. These pumps are diaphragm type, with adjustable stroke lengths that allow fine-tuning of the dispensing rate. The pumps are small, about the size of a coffee cup, but remarkably accurate, capable of metering within plus to 2% of the set point over a wide range of flow conditions. The pumps produce a rhythmic clicking sound as they operate, each click representing one stroke of the diaphragm. The pre-soak pump operates at 40 strokes per minute, the foam brush soap pump at 30 strokes per minute, the spot-free rinse conditioner pump at 12 strokes per minute, the wheel cleaner pump at 60 strokes per minute, and the drying agent pump at 15 strokes per minute. These different rates create a polyrhythmic pattern, with the clicks occurring at irregular intervals, but with an underlying mathematical relationship. Every 60 seconds, the pattern repeats. The pre-soak pump will have completed 40 strokes, the foam brush soap pump 30 strokes, the conditioner pump 12 strokes, the wheel cleaner pump 60 strokes, and the drying agent pump 15 strokes. It's like a clock made of chemistry, marking time in chemical doses rather than seconds. The chemical room is ventilated by a dedicated exhaust fan that runs continuously, maintaining a slight negative pressure to prevent any chemical vapors from migrating into other areas of the facility. The exhaust fan is a propeller type, 24 inches in diameter, moving 1,200 cubic feet of air per minute. It produces a steady whooshing sound, like wind through a tunnel, that serves as a sonic backdrop to the clicking of the metering pumps. Chemical. Levels in the storage containers are monitored by ultrasonic level sensors mounted on top of each container. These sensors emit ultrasonic pulses at 40 kHz, well above the range of human hearing, and measure the time it takes for the echo to return from the liquid surface. From this time measurement, the sensor calculates the distance to the liquid surface and, knowing the container geometry, determines the volume of chemical remaining. When a container reaches 20% capacity, the control system generates a low-level alarm, alerting the operators that a refill is needed. This gives sufficient lead time to order and receive fresh chemical before the container runs dry. The system tracks chemical usage patterns and can predict when refills will be needed, optimizing inventory management and reducing the risk of running out at an inconvenient time. It is now 8:43 p.m. The sun has been down for nearly 2 hours, and the car wash has processed its 47th vehicle of the evening shift. The pace of business has slowed. The last vehicle exited the tunnel 11 minutes ago, and the facility is in a state of ready standby, all systems running but not actively washing. In this quiet period, the sounds of the facility become more distinct, more individual. The high-pressure pump, which has been running continuously for over 2 hours, maintains its steady 60 Hz hum. The biological reactor aeration blower continues its higher-pitched tone at 400 Hz. The ventilation fan in the chemical room produces its constant whoosh. The chemical metering pumps click at their individual rates, waiting for the next vehicle to trigger their solenoid valves and release their carefully measured doses. The facility lighting is fluorescent. T8 lamps in 4-foot fixtures, 42 fixtures total distributed throughout the tunnel and equipment rooms. Each fixture contains 2 lamps, each lamp rated at 32 watts, drawing 0.26 amps at 120 volts. The lamps operate on electronic ballasts that run at 25 kHz, far above the audible range, eliminating the characteristic 120 Hz flicker and hum of older magnetic ballast systems. The lights cast a cool white illumination, 4100 Kelvin color temperature, creating an environment that is neither warm nor cold but neutral, industrial, purposeful. The concrete floors are polished and sealed, reflecting the light with a subtle sheen. The walls are painted epoxy-coated block, easy to clean, resistant to moisture and chemicals. At 9:15 p.m., a white Ford F-150 pickup truck enters the wash tunnel. The entry sensor detects its presence, and the PLC initiates the wash sequence. The high-pressure pump, which has been idling at low speed, spools up to full power. The pre-soak solenoid valves open, and the familiar whoosh of pressurized water fills the tunnel. The conveyor engages, and the truck begins its journey through the wash process. For the next 5 minutes and 47 seconds, the symphony repeats: pre-soak, foam brush, side brushes, wheel cleaning, spot-free rinse, drying. Each stage executes with mechanical precision, each component performing its designed function within its specified parameters. The reclamation system receives the runoff from this wash cycle and processes it just as it has processed every other gallon of water today. The sand filter removes suspended solids, the biological reactor consumes dissolved organics, the clarifier separates settled solids, and the storage tank receives clean, reclaimed water ready for the next cycle. It's a closed loop, nearly perfect in its efficiency. At midnight, when the last customer has departed and the facility enters its nightly shutdown mode, a different kind of activity begins. This is the automated cleaning cycle, where the car wash essentially washes itself. The PLC initiates this process automatically based on its internal clock. All vehicle washing operations cease, but the equipment systems remain active. The high-pressure pump continues to run, but now its output is directed through a different set of nozzles, self-cleaning nozzles mounted throughout the tunnel that spray water and cleaning solution across all internal surfaces. These nozzles are carefully positioned to reach every surface that might have accumulated dirt or chemical residue during the day's operations. There are 16 nozzles in the tunnel, 8 nozzles in the equipment room, and 4 nozzles in the chemical room. Each nozzle operates on a programmed sequence, spraying for 30 seconds, then pausing while the next nozzle activates, creating a progressive cleaning pattern that sweeps through the entire facility over a period of 40 minutes. The cleaning solution used in this cycle is a mild alkaline cleaner, formulated to dissolve oils and surfactants without damaging stainless steel, painted surfaces, or rubber components. It's dispensed at a concentration of 1.200, creating a solution that is effective but not overly aggressive. The sound of the self-cleaning cycle is different from the vehicle washing sounds. The nozzles operate at lower pressure, 400 psi instead of 1200 psi, and they're not directed at any solid surfaces that would produce splashing or spraying sounds. Instead, the water arcs through the air and lands on the sloped floors, flowing toward the drains with a gentle pattering sound. It's peaceful, this nightly ritual. The facility takes care of itself, maintaining its own cleanliness with the same systematic approach that it applies to the vehicles that pass through during the day. There's something almost meditative about it. The way the cleaning progresses from one zone to the next, methodical and thorough. After the chemical cleaning phase, there's a rinse phase. Fresh water flows through the same nozzles, flushing away the cleaning solution and leaving all surfaces clean and ready for the next day's operations. This rinse phase lasts 20 minutes, using approximately 80 gallons of water. Finally, at 1 Gs AM, the cleaning cycle completes. The nozzles shut off, the high-pressure pump winds down, the chemical metering pumps cease their clicking. The biological reactor aeration blower continues. It runs 24/7, but most other systems enter a low-power standby mode. The facility is quiet now, but not silent. There's still the hum of the aeration blower, the soft gurgle of water flowing through the biological reactor, the occasional click of a thermostat-controlled heater maintaining temperature in the chemical room. These are the sounds of systems, maintaining themselves, waiting for morning, ready to begin again. At 5:30 a.m., 90 minutes before the facility opens for business, the PLC initiates the morning startup sequence. This is a careful, methodical process designed to bring all systems online in the proper order, warming up motors, pressurizing lines, and verifying that all sensors and controls are functioning correctly. First to start, the high-pressure pump. It begins at idle speed, circulating water through the system, but not building full pressure. This allows the pump to warm up gradually, expanding the internal clearances and ensuring proper lubrication before full load is applied. After 3 minutes of idle operation, the pump gradually increases speed over a period of 2 minutes, reaching full 3,450 RPM operation at the 5-minute mark. Next, the reclamation system pumps. These start in sequence, 30 seconds apart, to avoid a sudden surge in electrical demand that might trip a circuit breaker. The drum filter pump starts first, then the sand filter feed pump, then the biological reactor recirculation pump, then the clarifier recirculation pump. Each motor produces its characteristic hum as it comes online, adding to the growing chorus of mechanical sound. The conveyor system initializes next. The PLC commands a test cycle, running the conveyor through its full range of motion at half speed, verifying that all rollers are turning freely and all chain drives are properly tensioned. This takes 2 minutes, and during this time, the facility is filled with the sound of rolling chains and humming motors, a mechanical awakening. The chemical metering pumps prime themselves, drawing chemical from their storage containers and filling their feed lines. This is important because air in the chemical lines would result in incorrect dosing during the first wash cycles of the day. Each pump runs for 60 seconds, expelling any air and ensuring that the lines are filled with liquid chemical right up to the solenoid valves. At 6 a.m., 1 hour before opening, all systems are online and operating normally. The facility conducts a self-test, with the PLC checking each sensor, each motor, each valve, verifying proper operation. Any faults would generate an alarm and be displayed on the operator interface panel. This morning, as on most mornings, all systems check out normal. The facility is ready for another day. The first employee arrives at 6:30 a.m. He walks through the facility, performing a visual inspection, checking chemical levels, verifying that the reclamation system is operating properly, looking for any signs of leaks, unusual wear, or other maintenance needs. Finding everything in order, he turns on the external lighting, a set of LED floodlights that illuminate the entry and exit areas and unlocks the gates. At 7 a.m., the facility opens for business. Within 5 minutes, the first vehicle of the day, a red Toyota Camry, enters the wash tunnel and the cycle begins anew. To truly appreciate the car wash, we must understand the chemistry at work in each stage of the process. This is not just water and soap. This is applied surface chemistry, the science of how molecules interact with surfaces to remove contaminants and leave them clean. The pre-soak solution is an alkaline detergent, formulated with multiple components working in synergy. The primary, active ingredients are alkylbenzene sulfonates, surfactants that reduce the surface tension of water, allowing it to spread and penetrate into layers of dirt. These molecules are amphiphilic. They have one end that's attracted to water, hydrophilic, and one end that's attracted to oils and greases, lipophilic. When the pre-soak solution contacts a dirty surface, the surfactant molecules arrange themselves at the interface between the dirt and the surface. The lipophilic ends penetrate into the oil or grease layer, while the hydrophilic ends remain in the water phase. As more and more surfactant molecules accumulate at the interface, they eventually surround the dirt particles, forming structures called micelles with the dirt encapsulated inside. These micelles are stable in water. They don't recombine into larger oil droplets, so the dirt remains suspended in the solution and can be rinsed away. This process is called emulsification, and it's fundamental to how detergents work. The pre-soak also contains chelating agents, specifically EDTA, ethylenidiamine tetraacetic acid, and its sodium salts. These molecules have the ability to bind to metal ions, calcium, magnesium, iron, forming stable complexes that prevent the metals from interfering with the surfactants. Hard water contains significant amounts of calcium and magnesium, and without chelating agents, these ions would react with the surfactants to form insoluble precipitates, soap scum. The chelating agents prevent this, ensuring that the detergent remains effective even in hard water. The alkaline builders in the Avis-Sechai formula, typically sodium carbonate and sodium metasilicate, serve multiple purposes. They boost the pH to the optimal range for surfactant activity, pH 11 to 12. They provide additional detergency through their own chemical action, and they create a buffering capacity that maintains the pH even as the solution becomes diluted or contaminated with acidic substances. The foam brush soap has a different chemistry. It's formulated to produce large volumes of stable foam, because foam serves both cleaning and visual purposes. The foam physically lifts dirt from the surface, holding it in suspension where it can be rinsed away, and it also provides a visual indication to the customer that cleaning is taking place. The foam is created by a combination of surfactants and foam stabilizers. The surfactants reduce surface tension, allowing air to be whipped into the solution to create bubbles. The foam stabilizers, typically fatty acids or their derivatives, form a protective layer around each bubble, slowing the drainage of liquid from the foam structure and preventing the bubbles from coalescing. Has a pH of 11.2, alkaline enough to break down oils and greases, but not so harsh as to damage paint or rubber seals. A dedicated pump, a centrifugal model spinning at 1,150 RPM, draws this solution from the tank and meters it into the water. Stream at a ratio of 1.120. For every 120 parts of water, 1 part of pre-soak concentrate. This mixing happens in a Venturi injector, a simple but elegant device with no moving parts. The water flows through a constricted section, creating a low-pressure zone that draws the chemical concentrate into the stream through a side port. Physics does all the work. The Venturi injector hums at a frequency determined by the flow rate and the dimensions of the constriction. Tonight, it's producing a tone at approximately 380 Hz, a slightly higher pitch than the water streams themselves, creating an acoustic beating pattern, a gentle wah-wah-wah-wah that pulses at about 4 cycles per second. It's hypnotic, this pulsing, like a slow heartbeat made of water and chemistry. The pre-soak solution hits the Honda Civic in overlapping patterns. The 14 side nozzles are aimed at precisely 23 degrees from horizontal, calculated to provide optimal coverage of the vehicle's lower panels, wheel wells, and rocker panels, the areas where road grime accumulates most heavily. The top 14 nozzles point straight down, covering the hood, roof, and trunk. The spray patterns overlap by 30%, ensuring that no area receives less than full coverage. The dwell time, the period during which the pre-soak remains on the vehicle before being rinsed, is calibrated to 45 seconds. This is not arbitrary. Laboratory testing has shown that the surfactants in the pre-soak formula require 38 seconds to fully penetrate and emulsify road film. 45 seconds provides a 7-second safety margin, accounting for variations in temperature and grime thickness. During these 45 seconds, the conveyor system continues to move the vehicle forward at a precisely controlled rate of 2.6 feet per minute. The conveyor is a roller system with polyurethane-coated rollers spaced every 18 inches along a 40-foot tunnel. Each roller is powered by a 1.2 horsepower motor through a chain drive system, creating a synchronized movement that is smooth and vibration-free. The sound of the conveyor is a low rumble, felt as much as heard. The roller motors produce a collective hum at 60 Hz, the same frequency as the electrical supply, but the chain drives add a subtle rhythmic component, a soft ch-ch-ch-ch as each link engages and disengages with the sprockets. There are 147 links in each chain section, and with the roller turning at 23 RPM, each link passes through the sprocket 3,181 times per hour. This creates a sonic texture, a granular quality to the sound that is oddly soothing, like distant rain on a tin roof. The Honda Civic moves forward, now 6 feet into the tunnel, its surface covered in a thin film of pre-soak solution. Tiny droplets run down the windows, following paths determined by gravity and surface tension, creating ephemeral streams that reflect the overhead lights in shifting, complex patterns. Now we arrive at the first brush, and this is where the wash becomes tactile, where chemical cleaning transitions to mechanical cleaning. The brush assembly is a rotating cylinder, 5 feet in diameter and 7 feet long, covered in thousands of individual foam bristles. But these are not ordinary bristles. Each bristle is made of closed-cell polyethylene foam, extruded through a die at precisely 340 degrees Fahrenheit, and then cooled in a water bath over a period of 12 seconds. This process creates a foam structure with cells that are 0.4 millimeters in average diameter, small enough to trap and remove dirt particles, but large enough to remain soft and flexible. The closed cell structure means that water and chemicals cannot penetrate into the foam, preventing the bristles from becoming waterlogged and heavy. The bristles are arranged in a helical pattern around the brush cylinder, with each bristle offset from its neighbors by 3.7 degrees of rotation. This creates a continuous, overlapping pattern of contact with the vehicle surface. There are exactly 1,296 bristles on this brush, 144 rows of 9 bristles each. The number is not accidental. It provides the optimal balance between cleaning effectiveness and brush longevity. The brush rotates at 125 RPM. This is a critical specification. Too slow, and the bristles don't generate enough scrubbing action to remove bonded contaminants. Too fast, and the bristles can create swirl marks in the paint's clear coat. 125 RPM is the sweet spot, determined through years of testing with paint thickness gauges and surface profilometers. At 125 RPM, each bristle makes contact with a given point on the vehicle surface 20.8 times per second. But the bristles are soft. They compress by up to 60% of their length when pressed against a surface. This compression means that each contact is gentle, more of a caress than a scrub, yet effective because of the sheer number of contacts occurring simultaneously. The brush is driven by a 5-horsepower motor through a gearbox with a 14.1 reduction ratio. The motor spins at 1,750 RPM, and the gearbox reduces this to exactly 125 RPM while increasing torque proportionally. The gearbox is a planetary design, with 3 planet gears orbiting a central sun gear, all enclosed in a housing filled with synthetic lubricant. The gears produce a soft whirring sound, a mechanical purr that blends with the deeper hum of the motor. As the brush makes contact with the Honda Civic, the sound changes. The foam bristles compress against the sheet metal of the hood, and you hear a soft swooshing sound, like corduroy being stroked in rhythm. Swoosh, 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 125 times per minute, while simultaneously each individual bristle adds its own tiny contribution to the sonic texture. It's a white noise, but with structure, with pattern, with intention. The brush moves laterally as it rotates, traveling along a horizontal rail that spans the width of the wash tunnel. This lateral motion is controlled by a servo motor and a precision ball screw assembly. The brush travels from the driver's side of the vehicle to the passenger side at a rate of 6 inches per second, ensuring complete coverage of the hood, roof, and trunk. When it reaches the end of its travel, a limit switch signals the servo to reverse direction, and the brush travels back across the vehicle at the same steady rate. This back-and-forth motion creates a Doppler effect in the sound. As the brush approaches, the pitch rises slightly, perhaps by 15 or 20 hertz, barely perceptible, but definitely present. As it moves away, the pitch drops by a corresponding amount. This gentle pitch modulation adds another layer of complexity to the soundscape, a subtle variation that prevents the audio from becoming monotonous. The brush assembly contains its own dedicated water supply system. 8 nozzles, embedded within the brush cylinder and protected by the foam bristles, deliver a steady stream of fresh water at 40 psi, much lower pressure than the pre-soak arch, because the purpose here is to lubricate and rinse, not to blast. The water flows at 2.2 gallons per minute, creating a gentle splashing sound as it mixes with the pre-soak solution being scrubbed from the vehicle's surface. Beneath the brush, a series of drain channels collect the runoff. These channels are molded fiberglass, sloped at exactly 2 degrees to ensure gravity-driven flow toward the collection sump. The water flows over the smooth fiberglass surface with a soft gurgling sound, like a small brook over rounded stones. This is not turbulent flow. The Reynolds number is around 1/800, placing it in the transitional region between laminar and turbulent flow, creating a complex acoustic signature that is part babble, part whisper. The Honda Civic spends 90 seconds under the first brush. During this time, the brush makes approximately 240 complete passes across the vehicle's upper surfaces. Each pass removes a microscopic layer of loosened grime, building incrementally toward a clean surface. It's a process that requires patience, repetition, and precision. As the Honda Civic continues its journey through the tunnel, it encounters the side brushes. These are vertical cylinders, 3 feet in diameter and 6 feet tall, positioned on both sides of the wash bay. Like the top brush, they are covered in closed-cell foam. Initially, the jet is cohesive, maintaining its circular cross-section. But within a few inches of the nozzle, surface tension forces are overcome by aerodynamic forces, and the jet begins to break up into droplets. This process is called atomization, and it's governed by the Weber number, a dimensionless parameter that relates inertial forces to surface tension forces. RV2D is where R is density, V is velocity, D is jet diameter, and S is surface tension. For our jets, 1000 Dawson X8362 X 0.01, 0.072, 97,000. Any Weber number above 100 indicates that the jet will rapidly atomize. Our jets are far above this threshold, which is why they create such a fine mist. The atomized droplets have diameters ranging from 50 to 500 microns, with a mean droplet size around 150 microns. These droplets have enough momentum to impact the vehicle surface with significant force, but they're small enough that the impact doesn't damage the paint. The impact force per unit area, pressure, can be estimated from P, RV22. This is the dynamic pressure, also called stagnation pressure. For our jets, P, 1000 x 83.62, 2, 3,494,000 don, PR, 507. PSI, this is the pressure exerted when the water stream impacts a surface and comes to a complete stop. It's sufficient to remove loosened dirt and debris, but well below the pressure that would damage automotive paint, typically 3000 psi. Now consider the foam brush water flow. This operates at much lower pressure, 40 psi, and flows through larger openings. The flow rate is 2.2 gallons per minute, distributed across 8 nozzles, so 0.275 gallons per minute per nozzle. Converting to metric, 0.275 GPM, Zurich 1.04 liters per minute, Zurich 17.3 milliliters per second, Zurich 17,300 cubic millimeters per second. If the U-Chester nozzle orifice is 3 millimeters in diameter, the cross-sectional area is A, Churtus PR2, Chub PX 1.52, Churtus 7.07 dimetum. The velocity is then V morph Ras QA morph rate, frames 7,300, 7 more 7, more 2,247 mate, frames 245 free, in most 8 feet per second. This is a gentle flow, just fast enough to overcome surface tension and form a continuous stream, but slow enough that it doesn't splash or create excessive turbulence. The Reynolds number for this flow is Re, Arvid, where M is dynamic viscosity of water. About 0.001 PAs at room temperature. Re, 1000 x 2.45 x 0.003, 0.01, 7,315. This is in the transitional range between laminar, Re 2300, and fully turbulent, Re 4000 flow. The flow exhibits some turbulent characteristics, but retains some degree of organization. It's a complex, interesting flow regime that produces a soothing visual and acoustic effect. The airflow from the drying blowers is fully turbulent, with velocities of 83 ms, 187 meni-taj, and characteristic dimensions on the order of meters. The Reynolds numbers are in the millions. This is chaotic flow, with eddies and vortices at all scales from millimeters to meters. The boundary layer on the vehicle surface during drying is extremely thin, on the order of 0.1 millimeters, because of the high velocity. Within this boundary layer, the velocity transitions from 0 at the surface, the no-slip condition, to full free-stream velocity just 0.1 millimeter away. The velocity gradient is enormous, 83 mètres, 0.01, $830,000 per second. This extreme velocity gradient creates high shear stress at the surface, and it's this shear stress that removes the water. The water forms a thin film on the surface, and the airflow exerts a tangential force on this film, pushing it along the surface and eventually off the edges. The shear stress can be estimated from T my m dv d, where dv dy is the velocity gradient. For air at room temperature, m 0.018 pace, so T m 0.018 x 830,000 15 P m 0.22. PSI, this might seem small, but it's acting on the thin water film, and it's sufficient to overcome the adhesive forces holding the water to the surface. The water sheets off, accelerates to high velocity, and is carried away by the airstream. The car wash is a significant consumer of electrical power. Let's examine the electrical infrastructure that makes it all possible. The facility is supplied with 3-phase electrical service at 480 volts, delivered through an underground conduit from a pad-mounted transformer located 50 feet from the building. The service entrance conductors are 250 MCM aluminum, capable of carrying 255 amps continuously. These conductors terminate in a 400 amp main breaker panel located in the electrical room. From this main panel, power is distributed to sub-panels and individual loads through a network of conduits and cable trays. The largest loads are the motors. The high-pressure pump motor at 35 horsepower draws 42 amps at 480 volts, 3-phase. The 3 drying blower motors, 15 horsepower each, draw 18 amps apiece. The Reclamation system pumps, conveyor motors, and brush motors collectively draw another 60 amps. Total connected motor load, approximately 180 amps. But motors don't run at full load all the time. Average electrical demand for the motors is about 65% of connected load, or 117 amps. This represents a power consumption of P 3XVXIXPSW, where V is voltage, 480 V, I is current, 117A, and PF is power factor, approximately 0.85 for motor loads. P, IBMOI 732, X 480, X 117, X 0.85, current 82,400 watts, 482.4. Over a 10-hour operating day, this is 824 kilowatt hours. At an average commercial electricity rate of 0.12 per kilowatt, the daily motor energy cost is $98.88, but motors aren't the only loads. Lighting accounts for about 3 kilowatts, control systems and computers, another 2 kilowatts. And the water heater and chemical heaters collectively consume 15 kilowatts, though these are intermittent loads, averaging perhaps 8 kilowatts over the operating day. Total average. Power consumption, 93 kilowatt or 930 kilowatt per operating day. Annual electricity consumption is approximately 280,000 kilowatts, costing about $33,600 per year. The electrical distribution system includes extensive monitoring. Current transformers on each major circuit provide feedback to the PLC, allowing continuous monitoring of power consumption. If a motor draws excessive current, indicating a mechanical problem, or insufficient current, indicating that it's not running, an alarm is generated. Power factor correction capacitors are installed at the main service entrance. These capacitors counteract the inductive reactance of the motor loads, improving the overall power factor from 0.75 without correction to 0.95 with correction. This reduces the current drawn from the utility by approximately 20%, resulting in lower demand charges and improved system efficiency. The capacitors are arranged in a switched bank, with contactors that engage or disengage capacitor stages based on the measured power factor. A power factor controller monitors the system continuously and switches capacitor stages as needed to maintain the target power factor of 0.95. When a capacitor stage switches, there's a distinctive sound, a sharp snap as the contactor closes, followed by a very brief hum at 120 Hz as the capacitor initially charges. The total capacitance of the bank is 150 kVAR, distributed across 3 stages of 50 kVAR each. Grounding and bonding are critical for electrical safety. All metal equipment frames, enclosures, and piping are bonded together and connected to a ground electrode system consisting of 8 ground rods, each 8 feet long and 5 to 8 inch in diameter, driven into the earth around the perimeter of the facility and connected by a copper ground ring buried 18 inches below grade. The ground system resistance is measured annually and is consistently below 5 ohms, well within the requirement of 25 ohms specified by the National Electrical Code. This low resistance ensures that fault currents can flow safely to ground, tripping over current protection devices quickly in the event of a ground fault. A car. Whoosh of this sophistication requires regular maintenance to ensure reliable operation. There is a detailed maintenance schedule programmed into the PLC's internal calendar that tracks when various maintenance tasks are due. Daily maintenance tasks performed by the morning operator, visual inspection of all equipment, check chemical levels and refill as needed. Verify that all pressure gauges read within normal range. Check for any leaks or unusual sounds. Review the previous day's alarm log, weekly maintenance tasks. Clean the pre-soak arch nozzles with a brush and dilute acid solution to remove mineral deposits. Inspect foam brush bristles for wear and replace if necessary. Check conveyor chain tension and adjust if needed. Clean the floor drains and remove any accumulated debris. Test the emergency stop system. Monthly maintenance tasks. Change the oil in the high-pressure pump gearbox, ISO 68 weight, 2 quarts. Inspect and clean the sand filter, backwash if necessary. Check motor bearings for proper lubrication and add grease if needed. Test all sensors and verify accurate readings. Calibrate the chemical metering pumps using a graduated cylinder and stopwatch quarterly maintenance tasks. Inspect and clean the biological reactor, remove any sludge accumulation. Test the reverse osmosis membrane performance and clean if conductivity has increased. Inspect electrical connections for tightness and signs of heating. Test ground fault protection devices, Review energy consumption data and identify any anomalies. Annual maintenance tasks. Complete inspection of all motor windings using a megohm meter. Replace foam brush bristles regardless of apparent condition. Drain and flush the water heater. Inspect the anode rod. Test backflow prevention devices. Comprehensive calibration of all pressure transducers and flow meters. Professional inspection of the electrical system by a licensed electrician. Measure ground system resistance. The maintenance schedule is comprehensive, but not burdensome. Most tasks can be completed in minutes rather than hours. The key is consistency, performing the maintenance on schedule, not deferring until problems develop. The facility maintains a detailed maintenance log, recorded in a database that tracks every maintenance activity by date, technician, time required, and materials used. This log serves multiple purposes. It provides a historical record for warranty claims, it helps identify recurring problems, and it serves as a training resource for new employees. Over the 3 years that this car wash has been in operation, the maintenance log shows excellent reliability. The high-pressure pump has required 1 seal replacement. The foam brushes have been replaced 4 times, every 9 months as scheduled. The reverse osmosis membranes are still original, with performance declining only slightly from the initial specification. The electrical system has required no repairs beyond routine replacement of a few indicator lamps and 1 photoelectric sensor that failed due to water intrusion. This reliability is a direct result of proper design, quality components, and rigorous maintenance. Infrastructure, when done right, is remarkably dependable. Let's consider the economics of operating this car wash. This is, after all, a business, and it must generate revenue sufficient to cover its operating costs and provide a return to its owners. The facility is open 70 hours per week, 7 days, x 10 hours per day. Average vehicle processing time is 6 minutes, including dwell time in the tunnel and the interval before the next vehicle enters. This gives a theoretical maximum throughput of 10 vehicles per hour or 700 vehicles per week. Actual throughput is lower due to gaps in demand. Average utilization is approximately 65%, meaning 455 washes per week. The wash price is $12 for a basic wash, with options to upgrade to premium washes at $18 or $25 that include additional services like wax application and tire shine. Average revenue per vehicle, accounting for the mix of basic and premium washes, is $15.80. Weekly revenue is thus $455 x $15.80, $7,189. Annual revenue is approximately $374,000. Operating costs break down as follows. Electricity, $33,600 per year, as calculated earlier. Water and sewer, $8,400 per year. Fresh water at $4 per 1,000 gallons. Sewer at the same rate. Chemicals, $24,000 per year, approximately $0.50 per vehicle wash. Labor, $85,000 per year, 2 part-time employees at $7 per hour. Maintenance, $12,000 per year, parts, supplies, and occasional contractor services. Insurance, $8,000 per year, liability and property coverage. Property tax, $6,000 per year, based on assessed value of land and improvements. Miscellaneous, $5,000 per year, office supplies, uniforms, cleaning supplies. Total operating costs, $182,000 per year, operating profit before debt service, $374,000, $182,000, $192,000 per year. The facility cost $850,000 to construct, financed with a commercial loan at 6.5% interest over 15 years. Annual debt service is approximately $89,000, leaving net profit of $103,000 per year. This is a healthy return on investment, about 12% annually on the equity invested, assuming 30% down payment of $255,000. The payback period is reasonable, and the business generates positive cash flow from the beginning. But profitability depends on maintaining high quality and operational efficiency. If customer satisfaction drops and volume declines by 20%, annual revenue falls to $299,000. Operating profit drops to $117,000, and net profit after debt service falls to just $28,000. a marginal return. This is why the infrastructure matters so much. Reliable equipment means fewer service interruptions. Quality washes mean satisfied customers who return regularly. Efficient water and chemical usage means controlled operating costs. All of these factors contribute to profitability. The facility owner has invested in quality, and it's paying off in consistent, reliable performance and steady customer traffic. There's a lesson here about the value of doing things right the first time, even if it costs more initially. Let's return to the subjective experience of being in the car wash, because ultimately, this is what the customer experiences and what makes the car wash more than just an industrial process. You approach the entry in your vehicle, and the first thing you notice is the transition from bright daylight to the more controlled lighting of the tunnel. The fluorescent fixtures cast a cool, even light that eliminates harsh shadows. It's a neutral space, neither warm nor cold, optimized for functionality. As you enter the tunnel and stop on the conveyor, you hear a beep, the photoelectric sensor detecting your presence, and then a mechanical clunk as the conveyor engages. You feel a gentle acceleration as your vehicle begins to move forward. The sensation is smooth, not jerky, because the conveyor motor is controlled by a variable frequency drive that ramps up the speed gradually. The pre-soak arch activates with a sudden whoosh, and you're surrounded by spray. The sound is loud, but not alarming. It's the sound of pressure being released, of energy being directed. Through the windshield, you see the spray patterns, overlapping streams of water and chemicals creating a translucent curtain that envelops your vehicle. Then comes the foam brush, and the sound changes to that soft, rhythmic swooshing as the bristles make contact with the hood. You can see the brush rotating through the windshield, a cylinder of blue foam spinning and oscillating, methodically working its way across the upper surfaces of your vehicle. The soap foam accumulates on the windshield, reducing visibility to just vague shapes and colors, creating a sense of enclosure, of being inside a process. The side brushes engage, and you feel a gentle buffeting as they press against the doors. The sensation is not harsh. The foam compresses, absorbing the impact. But it's present, a tactile confirmation that cleaning is happening. The sound is all around you now, swooshing, slapping, the underlying hum of motors and pumps, the gurgle of water flowing to the drains. Then the high-pressure wheel cleaning jets activate, and the sound intensifies dramatically. The focused streams scream past your ears, attacking the wheels with purposeful aggression. It's the loudest moment of the wash, but it's brief, 30 seconds, and then it's over, and the conveyor resumes its forward motion. The spot-free rinse is almost anticlimactic after the intensity of the wheel cleaning. The water patters gently on the roof and flows down the windows, washing away the remaining foam, revealing clean glass and paint underneath. The visibility returns and you can see the tunnel ahead, the exit approaching, and then the dryers. The sudden roar of air, the vehicle shaking slightly as the high-velocity streams strike it. Water flies off in sheets, visible in the air for brief moments before being swept away. The roar is all-encompassing, drowning out every other sound, a forceful conclusion to the gentle washing that preceded it. And then, suddenly, you're through. The noise cuts off as you exit the tunnel, and the blowers deactivate behind you. There's a moment of profound quiet, your ears ringing slightly from the noise, adjusting to the sudden absence of sound. And then you notice the birdsong, the traffic sounds from the street, the normal ambient noise of the world, but it all seems quieter, more distant after the intensity of the wash. You exit your vehicle and inspect the results. The paint is clean, the windows are clear, the wheels are bright. There are no spots, no streaks, no residue. It's a satisfying transformation, accomplished in less than 6 minutes through the application of water, chemistry, mechanics, and engineering. As evening approaches once again, the car wash continues its steady rhythm. Vehicles enter, are cleaned, and exit in a continuous flow. The machinery hums, clicks, whooshes, and roars in its mechanical symphony. The water reclamation system processes gallon after gallon. The biological reactor teams with microscopic life, the chemical pumps, meter their doses with precision. This is infrastructure at its finest, purposeful, efficient, reliable, and nearly invisible. Most people never think about the complexity behind a simple car wash. They see only the result, a clean vehicle, without appreciating the intricate dance of systems that makes it possible. But there is beauty here, if you know where to look. Beauty in the precision of the chemical formulations, in the efficiency of the water reclamation system, in the reliability of the PLC control system, in the acoustic texture of overlapping mechanical sounds. The high-pressure reciprocating pump, beating like a mechanical heart at 57.5 strokes per second, is a marvel of engineering. The closed-cell foam brushes, spinning at exactly 125 RPM to prevent clear coat damage, represent years of materials science and testing. The water reclamation system, recovering 85% of used water through a multi-stage process, demonstrates environmental responsibility. Each component, each system, each process has been optimized through iteration and experience. This car wash is the result of accumulated knowledge, of lessons learned from failures and successes, of continuous improvement toward a goal of perfect reliability and efficiency. In a world that often celebrates the flashy and new, there's something deeply satisfying about infrastructure that simply works. Day after day, year after year, washing vehicles to a consistent standard, consuming minimal resources, requiring minimal intervention. It's a quiet success, a background achievement that enables modern life without demanding recognition. The whoosh of the high-pressure water acts as white noise, masking other sounds, creating an acoustic space that is both present and soothing. The complex machinery provides a layer of interest for those who appreciate mechanical systems. The rhythmic, repetitive nature of the processes creates a meditative quality, a sense of time marked not by hours and minutes, but by wash cycles, in foam brushes and drying blowers. As you drift off to sleep tonight, imagine yourself in that wash tunnel, surrounded by the sounds and sensations of the cleaning process, the whoosh of water, the swoosh of brushes, the roar of dryers, the smell of chemicals and clean water, the vibration of the conveyor beneath your feet, the cool, even light of the fluorescent fixtures, the steady hum of motors and pumps working in harmony. Infrastructure is the foundation of civilization, the invisible systems that make modern life possible. The car wash is a small example, a microcosm of larger systems. Water treatment plants, power grids, transportation networks that we depend on every day. And in this small corner of the world, in this Valley Vista car wash, the infrastructure is performing flawlessly, serving its purpose with mechanical precision and quiet dignity. The pump pumps, the brushes brush, the dryers dry, cycle after cycle, day after day, year after year, whoosh, swoosh, roar, clean, sleep well.